Okay, welcome to the replay. Today we're doing something fun called Is It Physics or Is It Magic? Hey Jay Bunting, hey Monique, welcome. Hey Steve770, welcome to today's scope. Wow, nice to see lots of new faces. Okay, so what you're seeing right now is a balloon, obviously, and it doesn't look all that impressive, a blown up balloon. Hey Jennifer, but if I turn it around, what you'll see is that this balloon is actually open to the atmosphere. It is staying inflated, even though the end of it is completely open to the atmosphere. Wine Tom. So my question for you is, hey Daddy J. Actually, let me turn this around first to say hello. Hello, welcome everybody. So my name is Joe. I'm the physics program chair at Cabrillo College in Santa Cruz, California. And today I want to show you something cool. Awesome, James, thank you. Dana, thank you very much. I want to show you something cool and ask you, is it physics or is it magic? So again, I'll turn this around, show it to you, and then cool physics, we got a vote already. Then if it's physics, I'll explain the physics. If it's magic, I will teach you how to do the magic trick. Up is I have a plastic box that we made here, and inside I have a balloon, and the balloon is completely inflated even though the outside is always open to the atmosphere. It's always physics. Daddy J, so far it's physics, but I'm gonna show you soon something that you're not gonna know whether it's physics or Love Tribe in the building. Hey Dana, welcome, thank you so much. Okay, so I'll give you the answer. The answer is this is just really cool physics. What's happening is, let me give you a quick little recap or a quick little overview, and then I'll show you the demo. So right now, the fact that this balloon is open to the atmosphere means that the pressure inside the balloon is atmospheric pressure, which at sea level, 14.7 pounds per square inch. Now the pressure inside the glass is less than atmospheric pressure, so the total force acting on the balloon trying to compress it and the total force trying to inflate it from the air outside sums up to zero. Dark matter. We actually talked about that on Wednesday. So let me turn this around again. We'll show you the demo. Okay, so we've got this balloon here. Let me show you once I pull the plug, it deflates. So let me show you how this works. One, let me show you something cool. I bet you didn't know that you could blow up a balloon by, rather than adding air, removing air. So this is just an airtight box, except for this little hole in here. I can plug it up to make it airtight. What I'm gonna do is blow up the balloon, not by the traditional method of putting air inside the balloon. I'm going to remove air from inside the box. When I do that, the pressure inside the box is going to be much less than the pressure outside the box. The air inside the room is going to rush inside the balloon and inflate it. Again, what I'm doing is I'm removing the air, some of the air from inside the box. The atmospheric pressure from around the room is actually going to cause enough force to blow the balloon up. Pretty cool, huh? Okay, so let me show you the demo. I'm gonna blow up the balloon, and then I'm going to put the cork in here, and what you're gonna see is that the balloon will stay inflated. Pretty cool, huh? The balloon is still inflated inside the box, even though it's completely open to the atmosphere. If I pull the plug, the balloon deflates again. So let me show you one more time and then I'll explain in detail why this works. It's really just some pretty cool physics. Can you blow up the balloon with the plug-in? Oh, great question. So let me just tell you something funny. So this has to do with pressure. And a quick little overview. Way to remember this, or the way to think about this, is the ideal gas law. It says pressure times volume equals nRT. N is the number of moles, R is the ideal gas constant, and T is the temperature in Kelvin. But important thing for pressure is pressure depends upon the number of moles, the temperature, and the volume. And the big thing is volume goes up, pressure goes down. volume goes down, pressure goes up. So right now the air inside here is at atmospheric pressure. If I try and blow up the balloon, what I'm doing is I'm forcing the air inside the box to be in a smaller volume. When that happens, the pressure increases. And the pressure gets so big, it's extremely difficult to blow it up with the cork in. Watch. Can't blow it, I hurt myself. Can't blow it up anymore. And let me tell you something, we have actually broken 3 of these because students jammed in the cork really, really tight, tried to blow it up, and they had really good lung power, and they blew it up enough that the pressure inside increased enough that it literally exploded. We had 2 glass spheres similar to this, and it actually caused the glass sphere to pop. Okay, so let me show you this one more time and explain in detail what's happening. So right now, I have this open to the atmosphere, which means the pressure is going to remain at atmospheric pressure, because if the pressure inside the box increases, it's going to force air out. If the pressure inside the box decreases, air is going to rush in. So right now I'm going to blow up the balloon. The air inside the balloon is going to be at atmospheric pressure. The air inside the box is going to be at atmospheric pressure. Now, once I cap it, even though you didn't see it, what happened is the balloon compressed a little bit. And that's because I have, let me show you, crude little drawing. I've got air inside the box, which is initially at atmospheric pressure, 14.7 pounds per square inch. I've got air inside the balloon, also at atmospheric pressure, 14.7 pounds per square inch. The air is exerting equal force, pushing the balloon out, pushing the balloon in. However, balloons are elastic, and so it's almost like stretching a rubber band. There's also a force which is trying to compress the balloon. What happens is the balloon compresses a little bit. 14.7 pounds per square inch. Yes, balloon compresses a little bit. When that happens, the air inside the box is now in a bigger volume, so the pressure decreases. What ends up happening is the force of the air inside the box, which is at less than atmospheric pressure, and the force of the elasticity of the balloon exactly balances the force of the air in the balloon trying to inflate the balloon. Total net force is 0. Now, let's see if I can do this. How should I show you this? See if I can crank this up a bit. What you'll see is once I pull the plug, I don't know if you'll be able to see this, but the balloon will compress a teeny tiny bit. I'm going to cover this up, and what you'll see is the balloon move. And why it's moving is because the air pressure inside the box is less than atmospheric pressure. So outside atmospheric pressure, there's going to be a net force pushing some air in. So watch the balloon move a little bit. Again, I'm covering up the hole. That was air rushing inside the box. Now I'm going to cover it again, and what you'll hear is air rushing outside the balloon, because right now the pressure inside the box is atmospheric pressure, but I also have the elasticity of the balloon. Ready? I don't know if you could hear that. I'll try it again. I'm covering this, opening up the box. You see the balloon move a little bit as air rushes in. Now the air inside is at atmospheric pressure. Air inside the balloon is at atmospheric pressure, but I also have the elasticity of the balloon exerting sort of a compressing force. Now, again, listen, I'll count 1, 2, 3. 1, 2, 3. And some of the air rushed out. Okay, so that is a pretty cool little demonstration. Has to do with atmospheric pressure, air pressure, and big thing is pressure depends upon the number of moles. As N goes up, pressure goes up. Temperature, as temperature goes up, pressure goes up. And volume. Now, as volume goes up, pressure goes down. So it happened here, and I'll do this one more time. Anytime something is open to the atmosphere, the air pressure has to be atmospheric pressure. Because if the pressure was bigger, it would drive air out. If the pressure was smaller, air would rush in. So initially, when I blow this up, since this hole is still open, the air inside the box is at atmospheric pressure. Same thing with the air inside the balloon. Once I cap this, A little bit of air rushed out of the balloon shrunk in size, which means the air inside the box is now in a bigger volume. The pressure decreased a little bit. So the amount of force pushing the balloon in got smaller, but the force of the air trying to compress the balloon plus the elasticity of the balloon trying to compress it exactly balances the force of the air inside the balloon trying to expand it. The net force is 0. Okay. That was today's Is It Physics or Is It Magic? I hope you enjoyed it. My name is Joe. I'm the physics program chair at Cabrillo College in Santa Cruz, California. Today is day 51 of my 1-year Periscope challenge. I made a commitment to get on Periscope every single day and share daily doses of dopamine through education, entertainment, and inspiration. If you did enjoy this, we're doing a weekly series on Wednesdays called Ask a Physicist Anything, with one of the instructors here, Paul Graham, who's just an awesome, awesome instructor. Where were you, my science? Why were you in my science teacher when I? Thank you. Last week we talked about dark matter and black holes. Wednesday we're going to touch on the physics of interstellar, and somebody wanted to know about. I'm forgetting what they wanted to know about. Totally forgetting. But Wednesdays, Ask a Physicist Anything. So if you enjoyed this, please follow me, share this with your friends. Thanks, Joe. Keep on rocking. You're so welcome. Before I leave, are there any quick questions that I can answer about this demonstration? No, great. Reina TV, thank you. I enjoyed it. Okay, well, I appreciate you stopping by. I'm here every day. YouTubes, yes, so I archive all of these on my YouTube channel. Just search for Joe McCullough, and you'll see every Periscope that I've done. And I also do a weekly blog on accelerated learning techniques and life skills. Have a phenomenal day. Dana, you too. Thank you so much for tuning in, and I hope to see you tomorrow. What if you connect both holes? I'm not sure what you mean by connect both holes, but once I cover this up, show you this one more time. I can never seem to do a short scope. These always drag on a little bit. So if I cover up this hole and remove this, what you're going to see is air rushing in because the air inside the box is less than atmospheric pressure. Let me just see if I can, how can I adjust this? Still complaining here. Hey, I made it to day 3. If anybody's not knowing what I'm talking about, I'm doing a 21-day no complaint experiment. The goal is to go 21 straight days without a single complaint. I've gone 3 days so far. Hey, named Marcus, you just missed it. I'm about to tune out, but do a quick little recap. So I've got a balloon which is remaining blown up, even though it's open to the atmosphere. Now, if I remove this cork while I keep this covered, what you'll see is the balloon move because air is rushing in. And once I cover this up and remove my hand, you'll hear air rushing out. The reason this balloon stays inflated is because the total net force on the balloon is 0. I've got air inside the balloon at atmospheric pressure. I've got air inside the box at less than atmospheric pressure, but I also have the elasticity of the balloon, and those 3 forces sum together to produce a net force of 0. Okay, thank you again for those of you joining. My name is Joe. I appreciate you spending some time with me, and I hope to see you all tomorrow. Thanks so much.